In this video, we will explain about control organization. Reference textbook is Digital Logic and Computer Design by M. Morris Mano, 10th chapter. So this is a typical digital system. In a digital system, we have control logic part and a data processor part. This data processor part will receive input data, then process that data by performing some set of micro operations that will generate output data. Then also that will affect some status register or status flags. Then the control logic that will responsible for generating control signals, and that will initiate the micro operations within the data processor. The inputs, different inputs to the control logic are external inputs and also status information or condition from the data processor. Next, we have to design the control logic part in a digital system. Design methods that use state and excitation tables can be used in theory, but in practice they are cumbersome and difficult to manage. So experienced designers use specialized methods for control logic design. In our case, in our examples, we will use an extension of the classical sequential logic method combined with a register transfer method. We are discussing about four methods: one flip-flop per state method, sequence register and decoder method, PLA control, microprogram control. So first we can consider the first two ones, that is these two. They have some similarities: one flip-flop per state method and a sequence register and decoder method. Then we will just discuss about the PLA control and a microprogram control because they have some similarity. One flip-flop per state method and a sequence register and a decoder method. This will result in a circuit that must use SSI or small scale integration and a MSI medium scale integration circuits for the implementation. The various circuits are interconnected by wires to form the control network. So this will form a hardwired control. If any alterations or modifications are needed, the circuits must be rewired to fulfill the new requirements. Next, we can consider PLA control and a microprogram control. This will use an LSI device, that is large scale integration device, such as programmable logic array PLA or a read-only memory. Any alterations or modifications in a microprogram control can be easily achieved without wiring changes, but by simply removing the ROM from its socket and inserting another ROM programmed to fulfill the new specifications. First, we can discuss in detail about one flip-flop per state method. Uses one flip-flop per state in the control sequential circuit. In the case of a circuit digital system, we can have different states that will change the state based on the present state and also some external inputs. Only one flip-flop is set at any particular time, all others are cleared. A single bit is made to propagate from one flip-flop to the other under the control of design logic. Each flip-flop represents a state and is activated only when the control bit is transferred to it. The advantage of one flip-flop per state method is design simplicity. We can easily design it. Disadvantage: uses a maximum number of flip-flops. Okay. For example, if we have 16 states, then we need 16 flip-flops here. Actually, we need four flip-flops to represent 16 states, because with the 4 bits we can have 2 to the power 4 16 different representations. But here we will use one flip-flop per state. So this is the control logic corresponding to a 4 state with 4 states, control logic with a 4 state or 4 state sequential control logic. Here we are using 4 D type flip flops, and these are the 4 D type flip flops, and all are connected with a decision logic. So the D inputs are connected with the decision logic, this one and this one, and a common clock pulse is given to all the D flip flops, and T0, T1, T2, T3, they are the outputs from the D flip flops, and they are also connected to this as inputs to the decision logic. Here and here, all these are these T outputs are connected as inputs to the decision logic. Then some external input signals are given to this decision logic. Then this is other set of control outputs. One flip flop per state. At any given time interval between two clock pulses, only one flip flop is equal to 1 and all others will become 0. Okay. So assume that this flip flop is 1. So here T output will be 1, all others are 0. Then this will represent a state. For example, 0 0 1. This is the state 0 0 1. And if we already said that only one of them will become one of the flip flop will become 1 and all others will become 0. So another state is, if this flip flop is 1 and all others are 0, this represents another state 0 0 1 0. Okay. Then this represents another state 0 1 0 0. Then this corresponds to, that is, this flip flop is 1 and all others are 0, this corresponds to another state. So we can have 4 states by using this method. Okay. The transition from present state to the next state is a function of the present state and certain input conditions. Okay. Each of the flip flop output is connected to the data processing section of the digital system to initiate certain micro operations. Then there is also some other set of control output that is also connected with the data processor component or data processor unit. So we can consider a simple example that can be implemented by our using one flip flop per state method. This is our problem. Implement with hardware the addition and subtraction of two fixed point binary numbers represented in sign magnitude form. The final result is to be in sign magnitude form. Result is also to be in sign magnitude form. So before that, we can consider or refresh our sign magnitude representation. This is used for representing signed numbers. Here, if there are n bits, then n minus 1 bits are used for storing the magnitude of the number, and 1 bit is used for storing sign. So for a positive number, sign bit will be 0, and for negative number, the sign bit will be a 1. For example, to represent plus 9. So this is a positive number, so the sign bit will be 0. And the magnitude will be represented like, assume that we are using 8-bit representation. So 7 bits are used for magnitude and 1 bit for sign. So 0 0 0 0 1 0 0 1. This is the magnitude. That is the binary equivalent of 9. Then in the case of minus 9, we will store a 1 here, that indicates minus value, and the same value will be stored in magnitude position. That is the binary equivalent of 9. 0 0 0 1 0 0 0 1. So total, we assume that total bits are 8 bits and 7 bits are used for storing magnitude and 1 bit for storing sign. The design is carried out in 5 consecutive steps. Step number 1 is the problem is stated. Step number 2, an initial equipment configuration is assumed. Step number 3, an algorithm is formulated. Step number 4, the data processor part is specified. Step number 5, the control logic is designed. First statement of the problem. Implement with hardware the addition and subtraction of two fixed point binary numbers represented in sign magnitude form. Complement arithmetic may be used provided the final result is in sign magnitude form. So next is equipment configuration. So this one is the equipment configuration corresponding to our problem. So we have a B register, that is a sign magnitude representation is used for B register. So we have this one is the magnitude of the B register, and this one is the sign bit. BS is the sign bit. Similarly, A register, n-1 bits are used for magnitude, and this one is our sign bit corresponding to A register. Then another part is ALU. This ALU will perform operations on these registers, and the result will be stored in A register, and the carry from this ALU, carry after operation, arithmetic operation, will be stored into this E bit. This E bit is used for storing the carry out from the ALU. The result will be stored in A register. Okay, the result after performing operation on A and B, the result will be stored in A register, and carry will be stored here. Okay. Then this part is the control logic part. This we have to design, and inputs to the control logic are two inputs. They are external inputs. So inputs coming from external circuits. One is QA and other is QS. If QA is equal to 1, that indicates an addition to be performed or an addition to be initiated. If QS is equal to 1, that indicates a subtraction is to be performed or initiated. So after initiating this addition or subtraction, this will perform the operation, and after completing that operation, that will be informed through the X output. This is an output signal to the external circuit. Operation terminated. So next we have to derive the algorithm. We designate the magnitude of two numbers by A and B. When numbers are added or subtracted algebraically, we find that there are 8 conditions to consider depending on the sign of the numbers and the operation performed. So for example, A, that can be represented in a compact form like this: plus or minus A, add or subtract, plus or minus B. So this is the compact representation. So here we have 8 permutation corresponding to this one, or 8 conditions to consider. But if the arithmetic operation is specified as a subtraction, we change the sign of B and add. In our example, what we will do is, if the operation to be performed is a subtraction, then we will simply change the sign of this one, and the operation will perform an add operation like this. If plus or minus A minus plus B, we can write that as plus or minus A plus minus B. Similarly, plus or minus A minus B can be written as plus or minus A plus B. So we have reduced these two operations into addition operation. This reduces the number of possible conditions to 4 from 8. Okay. Plus or minus A plus or minus B. Okay. Okay, we can derive a flowchart from this. Then this represents initial state, and if QS is equal to 1, that indicates subtract operation to be performed. Then we already said that the subtract operation, we have to reduce that subtract operation into an addition by simply changing the sign of the B operand. So BS is equal to B complement. The sign bit is complemented here if it is a subtract operation, and if addition operation, then this is directly given to here. There is a bypass to this step. Then next step is compare the sign bits of the two operands. If they are equal, then we have to simply add the magnitudes, that is A gives A plus B, and if there is the carry will be stored into E here. and then goes to the initial state, and x will become 1. So that will be given to the external circuit. So external circuit will identify that okay, the operation is now complete. Then if AS and BS, these are the sign bits, they are different, not equal. In that case, we need to subtract B from A, or we have to perform A minus B. That is here, that is mentioned here. A is equal to A plus B bar plus 1. B bar plus 1 means complement of B, 2's complement of B, or this is the equivalent to subtract operation. That can be done by using our ALU. Okay, and E is equal to carry out. Okay, and after performing the subtract operation, we will check for the E. If the value of E is equal to 1, that indicates A is greater than or equal to B. Then the result will be in correct form, because we are performing A minus B and A is greater than or equal to B. In that case, we are simply setting the E value as 0, and then go to initial state, and the result will be available in A register, and the sign of the result will be same as AS. Okay. Then if E is equal to 0, that indicates A is less than B. So in that case, if we are performing A minus B, what will happen? The content of the A will be not in correct form, because in our case we have to use a sign magnitude representation, but this will be in a 2's complement form. So what we have to do is, we have to find the 2's complement of A. But in the case of our ALU, we cannot find the 2's complement of a single register. Okay, then what we can do, we will first perform the 1's complement and then perform an increment operation, that we are doing here. So A is equal to A complement, then A is equal to A plus 1. So that in effect that will do a 2's complement. Now the content of the A will become into a positive form. Okay. Then we have to invert the sign bit. AS is equal to AS complement. Okay. Then we will go to the initial state again, and X will become, and make the X is equal to 1. So the operation terminated, signal will be given to external circuit. And from this we can easily derive an algorithm from this flowchart. Actually this flowchart itself is an algorithm. Then data processor specification, that is the next step. So this is our ALU and B register. BS is our sign bit corresponding to B register. This is the magnitude part, and this part is the magnitude for A register, and this is the sign bit. Then here we are using an ALU that we have already designed in our previous section, or in chapter 9, and the operations performed by this ALU are given in the table 9.4 of textbook, our reference textbook. So this S0, S1, S2, that will form the select lines, and Cin is also form another select line. Based on this input data, variables, this ALU will perform operation, and that will be stored into A register, that is A and B. The operation will be performed on A and B, and the result will be stored back into A register. But that is controlled by a load input. If the value of this L or load input is a 0, then this result will not be captured into A register, and if it is equal to 1, then the result will be captured here. Similarly, this load input is given as a control signal to E also. So the C out or the carry out from the ALU will be stored into the E bit only if L is equal to active, load signal is equal to active, otherwise that will not be captured. Then Y and Z, these control signals will invert the sign bits. If it is activated, then the value will become inverted. If it is 0, this will become 1. If it is a 1, then 1 bit will become 0. So just complement the sign bits, that is the function. Then this W is to clear the E bit. If you are giving or activating this W, the E bit will be cleared or will become 0. That is our data processor specification. Then control logic. This is the diagram corresponding to our control logic, the specification corresponding to our control logic. So next we can consider the control logic. This is our control logic. Then we have this receives 5 inputs, 2 from external environment and 3 from the data processor. These QA and QS are inputs from external environment. This corresponds to addition and this corresponds to subtract operation. Then another one is the E bit. E bit is actually this one. Okay, this one. So E bit. Then AS and BS, these are the sign bits of the A register and B register. They are XORed here to form a new signal S for simplicity, and if both have the same sign, this will become 0, and they have different signs, this will become a 1. Okay. Then this X corresponds to this an output to external circuit. This corresponds to the operation terminated or completed. Then S0, S1, S2, these are and input carry. This also, this will form our selection variables to our ALU. This L, Y, Z and W are outputs that go to the registers in the data processor as specified in the diagram. So L load A and E from ALU, Y complement BS, Z complement AS, then W clear A. Okay.